Hmm. One. Okay. Hi, everybody. Can you hear me?
Yep, got you, Yoni.
Thanks, TJ. All right. That's one thing out of the way. We've got voice. Next thing, iPad. All right, 11 p.m. Hi, STAT3004-STAT7304. Welcome. So a few things. So on the course website, you'll see I've updated the due date of Project 2, but I must apologize, I still didn't put Project 2 up. It will take me another day to do that. So that Project 2 is due on May 27th. I hope that gives us enough time. It means that the problem set, the final problem set, there's only kind of a week between the submission time of Project 2 and the problem set. I won't make the problem set too extensive. So that should be something that's doable in a week. You'll have the problem set way earlier. I've also updated the self-study guide. So if you go to, and that's what we'll speak about today mostly. Kind of overview the self-study guide, of course, with content. So now you've got activity 7 and activity 8 in quite detail, and these are the two activities that are taking you through Project 2. Okay, so let's go and start doing that. Are there any questions in general?
Yoni, just the lecture video from Friday. I didn't see that online yet.
I thought I put it online. Did I not? Okay, so let me.
I think you put an NBC NewsHour up online by mistake.
That cannot be. Really? Oh, I might have added that to the. Okay, I'm messing up with the play. Let me. Okay, I'll look at it after this lecture as I put this one on. So thanks for telling me. No, don't look at NBC NewsHour. That's rubbish. Other things. So the good news is that retired Professor Daryl Daly, my friend, one of the co-authors of EM3, is willing to read one of the projects. So that you handed in. I mean, the projects are very nice. So we'll see whose it is, but one of you guys will have feedback directly from the author of EM, of the book by Daryl Daly and Joe Gunn. All right, so let's look at activity 7, basics of continuous time Markov chains. So the first thing is this thing, the section 4.1 definition and examples, and I think that's where we stopped. So we'll just go through that. But notice there's just quite a lot of detail here. There's some skim, some read, some putting you into the code examples of the Statistics with Julia book, a bit of a digression to the Norris book, to Markov chains, but most of it is basically the SP4 chapter. So the most common thing they have in this activity is the SP4 chapter, and that's what you learn about continuous time Markov chains. And the next activity is all about chapter EM3, which is the focus of the second project. And the second project has two models, SIS and SIR. Okay, SIS, susceptible, infected, susceptible, infected, susceptible, infected, susceptible, infected, kind of like with the common cold. SIR, susceptible, infected, removed. Removed can be removed or recovered, depending. Okay, that's SIR. So that's what we do. All right, so let's start running on section 4.1, 4.2, and then we'll see how far we get. All right. So we're looking at SP4, I guess. We skipped the chapter SP3. SP3 was about renewal processes. I said what a renewal process is. It's generalization of a Poisson process where the time between events are not necessarily exponential random variables. And I think this is where we stopped Friday. So we looked at this property of which you'd call the Markov property of a process in continuous time. So if you have a stochastic process that takes discrete values, yeah, but it's defined in continuous time, T is a continuous time index, and if you know the value of the process in time S, you know that it was I, and you know a bunch of history. Let me put the history here in green. Then that history doesn't matter. The other thing is homogeneity. If you look at the difference between this time and this time, that difference is T. Okay, and then that means it's just like thinking that at time 0 you're in that state I. Okay, that state I that's here. All right. So the way that this section starts, it looks at the Poisson process, which I think by now you kind of have a feel for, and it considers the Poisson process to be a continuous time Markov chain. Okay, well, not exactly. It does the following. So if you look at this example, so you take a Poisson process, okay, and you take any discrete time Markov chain, Y and discrete time Markov chain with transition probability Uij. Okay, so, and now you make a continuous time chain from that as follows, or you make a continuous time process as follows. So look at this transformation. So you're taking your discrete time object, Y at time n, but instead of time n, you'll now stick in here the time index n of t, where n of t is the number of events that occur in a Poisson process up to time t. And you call this thing x of t, okay? Now, this thing is in its own right is going to be a continuous time Markov chain. Okay, so the one way, if you just want to kind of pictorially see what has happened here, is you could think of, this is your time, discrete time process. So let's say it's this weather chain that's going between state 1, 2, 1, 3, 2, 3, etc. Okay, and what you've done now, and this is kind of time n, this is discrete time, okay, and that's x, or I should call this, yeah, that's y of n, I'll call this y of n. What you've got here is y of n of t, okay, and you've got a continuous time process. Now, the time between events now, instead of taking them to be at unit distance like they are here, this is unit distance, you're going to take them as exponential random variables. So each one is going to be exponentially distributed with the rate lambda, but the same rate, okay? So now you're basically going to do like you'll be at a state up to here, and then you'll make a jump to state 2. Then you'll be at, let's say, a state up to here, and then you'll make a jump back to state 1. So this thing that you see here, this interval maps to this interval. And this interval that you see here maps to this interval. You see you're now at state, mistake, sorry. Let me undo that. So this is kind of where it starts. So this interval, actually this interval maps to this interval. And then this interval is this interval, etc. So you're basically scaling time according to exponential random variables. Okay. Now, some of you might be seeing it and saying, oh, okay, that's kind of neat. So you've taken your discrete time process and made it a continuous time process. However, there was quite a constraint here, right? What was the constraint? All the random variables had the same rate lambda. Okay, so all the time between events had the same rate lambda. All the continuous time Markov chain is really going to do is going to allow us to make that duration between events depend on the state where the transition is being made. Okay, I hope that's giving you a bit of an intuition for what's to come. All right. Now you want to speak, we already spoke about the transition probability, I think when we finished last time. So PTij is now at time after t units. So there was t units, t is any continuous time, okay? Any continuous time increment, going from state I to state j. That's what you call this. Now, you can actually see that for this Poissonification, this neat example that Poissonifies a discrete time Markov chain, and try to verify this yourself, you can actually compute this PTij to be the following. What you're going to do is you're going to take Uij to the, it's not to the nth power, okay? This is the nth power of the transition probability, okay? So it's not taking Uij, it's taking after n steps from I to j, okay? And then you're going to go from state I to state j, and you do here law of total probability with a Poisson random variable. Okay, so study this yourself and see that it makes sense. And then what we want is the Chapman-Kolmogorov equation. Okay, so the Chapman-Kolmogorov equation is just like it was in discrete time. What we're doing here is we're taking the time interval 0 up to s, and then we're taking it up to s plus t. Okay, so this duration here is of length t, and we're saying the probability of going from state I to state j, yeah, from state I to state j in s plus t time intervals is, well, in s plus t time units, you can look at all of the steps of going from I to k, and you can be in any intermediate state here, k can be anything, so you're summing over all possible k, and then going k to j. Okay, so that's the Chapman-Kolmogorov equation in continuous time. All right, so, and look at this proof. And I expect that by the visit hour next week, you'll probably ask me a few questions about the proof if needed, etc. Okay. Now, when you look at it, if you look at equation 4.1 here below, so we haven't looked at it, but let's look at it now, then there is an important quantity when you're speaking about continuous time Markov chains. And that important quantity is called the transition rate, or the jump rate from state I to state j. Okay, that's a jump rate from state I to state j. Now, the way you view this jump rate is once you've defined the transition probability from I to j over step h, then now think about a very small h. Okay, so think about h as h is going to 0. And of course, if h is 0, then p0 ij is 0 if I not equaling to j, or 1 if I equals to j, right? Because in 0 time units, you're not going to go between state I to state j if I is not j. However, if you take h small and normalize by h, then you get this qij. Okay, so the derivative of phij as h goes to 0. Okay, and qij is called the rate. The way to view a rate pictoriously is also to think of, you're now in state I, and you can go to state j or to state k or to state l. You've got these three alternative states. What you're doing at any micro instance of duration h, okay, h is like your very small number, right? H is like your 10 to the minus 6, so something that on the limit you're going to take to 0, is with probability qij times h, you'll make a transition I to j. And with probability qij, q high k, a different thing, k times h, you'll make a transition I to k. And with probability qil times h, you'll make a transition I to l. Okay, so you've got these kind of these independent micro trials that pull you either here or here or here to any other state. Now, with very high probability and every time h, what are you going to do? You're just not going to make any transition at all. Okay, that's what's going to happen with very high probability. But with these small probabilities, you'll make transitions, and these are rates of transitions. Okay. All right. Now you can, as you describe these things, you'll see, and we'll see this a bit more. You get the notation of little o of h popping up. So who here has seen big O notation, little o notation, any O notation? You guys know what I'm speaking about? Big O notation, little O notation.
I've seen it, but always confused the hell out of me. So.
Okay, that's good. Okay, some have seen big O. Okay, so some of you are doing computer science, right? And you've seen big O. Some of you are doing, I know some of you at least are doing the course asymptotic analysis. That's a fourth year course with Tony Roberts, maybe. So in general, just this general notation, let's, what can I do here? We are here. Let's do a little add page here. So in general, when you speak about little o of something, so I'll do like little o of x squared, and you can do a big O of x squared, okay? For example. So what you put in here is you put some function, okay? You put a little o function, big O of a function, etc. Now, when you're doing this, you kind of have to say on the sign, you have to say, hey, what am I speaking about? Am I going to speak about limit of x going to 0 or limit x going to infinity? Okay, so for example, when you're doing computer science, you often speak about limit x going to infinity because you want to kind of speak about this kind of sample sizes or let's say the problem sizes going large. Now here we're speaking about limit x going to 0. Okay, now when you speak about little o of x squared, what you're saying is if a function f of x, you'll say is in little o of x squared as limit x going to 0, then what you mean is that limit x going to 0 of that function divided by x squared goes to 0, the number 0. Okay, it means that the function f of x. So this is, I've told you here a few things. So first of all, this is a set of functions. Okay, it's a set of functions, and a priori we've agreed we're speaking about limit x going to 0. I mean, you'll see in other contexts in computer science, etc., limit x going to infinity. Okay, and we're speaking here about functions such that if you divide them by x squared and you take that function, that's going to 0. For example, here, let me give you one such function. One such function can be, you know, x to the power 1.5. Okay, all right. So x to the power 1.5 is in the set of function little o of x squared. Okay, so that's what you mean by little o notation. If you were speaking about big O notation, which we're not speaking about in this course, then what you'd mean is that as you do this, then the function goes to well, it depends. There are a few different interpretations, but some interpretation is that this actually goes to a constant. Okay. And you know, in general, you're kind of speaking about the class of functions that grow as like x squared or up to the size of x squared. But this is kind of what's important to us. And the only thing we're really going to see are these little O of h's. Okay. And here it's, so I said a whole bunch of words, but it's even written for us in the book. So when we divide it by h, it tends to 0 as h tends to 0. Okay, so little o of h is something that is less significant than the linear function. Now, this thing is important because it allows us to make sense of these types of things that I said here informally. So I said informally that you're going to speak about little kind of micro experiments, where each micro experiments is going to be, in a time duration h. I mean, think of it as 10 to the minus 6, but of course we're doing here mathematics. H can be arbitrarily small, okay? And when you're doing qij times h, you roughly would go from I to j with this probability, okay? Now, to make things precise, what you want to do is you want to say you're roughly going to go to this probability plus a little o of h. So little o of h is kind of your error, okay? Well, not sure if I really help with this, but this is the first thing to kind of say about this little o of h, and we'll see it more appearing, okay? We could have also defined the Poisson process with transition probabilities that had little o of h in them. Okay. So now if we go to example 4.2, example 4.2 is just a Poisson process, okay? Just a Poisson process. And if you want to treat the Poisson process as a continuous time Markov chain, then what you'll say, well, it's a continuous time Markov chain where the rate of going from state n to state n plus 1 is lambda, okay? Now, and we also know that the rate of going from I to j is 0 when j does not equal I plus 1. So basically, the only possible transitions in a Poisson process are going from state I to state I plus 1, or from state n to state n plus 1. Okay, so that's an example of a continuous time Markov chain. Before, when we saw it in the previous chapter, or 2 chapters ago in this book, we saw a Poisson process as a point process, but we can treat it as a continuous time Markov chain. Is a state space of the what's a state space of the Poisson process? The positive reals, well, it's indeed unbounded, but a Poisson process is just going to take, so thanks Mathusa, but the Poisson process it's not positive reals, it's positive integers, okay? So in general, all our continuous time Markov chains, we're going to speak about state spaces that are at most countable, but the positive reals are an uncountable set. Okay, here's the next example, and there's actually a full section devoted to these types of examples that deal with queuing theory. Okay, this example is called the MMS queue. So I'll actually skip this now and get back to it a bit later when we speak about queuing theory. When we speak about queue, just to be clear, this is a queue of people standing in line, or of packets waiting to be served, or assignments waiting to be marked, or patients waiting to be treated in the hospital. Okay, and the field of queuing theory is intimately connected with Markov chains and stochastic processes because they're stochastic models for these things. Without looking at the actual interpretation of the example, let's just look at this. So here we have a specification of going from state n to state n minus 1, okay? And that is going to be either the number, the state n times mu, if n is less than or equal to s, some fixed quantity, which is the number of servers, number of people treating you in the queue, or it's going to be s times mu. Okay, so that's actually part of this specification of the continuous time Markov chain. Okay, but here's an example that's much closer to your heart. I mean, it's closer to your heart because you started this course with branching processes, and clearly your heart was there. So remember, our branching processes were in discrete time, and that was somewhat unsatisfying to have branching process in discrete time, right? I mean, it's satisfying if you really know that you're living kind of within seasons or within generations. But if you're speaking, for example, about virus growth, or let's hope virus decay, then continuous time is a much more natural quantity. So here's how you would do it. Your state n would be the number of individuals in the population. Okay, it can be also the number of infected individuals if you'd like. All right. And you'd make a transition from state n to state n plus 1 just at a rate that's proportional to n, okay? Lambda times n. Okay. And you'd make a transition from n to n minus 1 also at a rate that's proportional to n, that's mu times n. Okay, so you're here, you can view it like this. You can take here, you can take time, say this is time, okay? And let's say you're at some given time here. There's some history here, we're not sure exactly what it was, okay? And you've got like 10 people in the system right now, or 10 infected individuals or something like that. So this is gonna stay for a while, but with probability lambda n, we will go up here. And with probability, well, sorry, with rate lambda n. So in every delta t and every h, lambda n time h will go up here. And the probability mu n or mu 10 will go here. Okay, so, and then we'll make a transition that will go either up or down. Okay, we'll go either here or here, and the thing will continue. Okay, so these are kind of motivating examples, and now we're asking how we construct the chain. Okay, so the thing to do here is to say, if you think of these rates, of these QIJs as kind of rates of coin flips, okay, these QIJs of rates of coin flips, then you'll say, well, you can have a coin flip that puts you there, you can have a coin flip that puts you there, you can have a coin flip that puts you there. So add up all the rates, and that's the total rate of actually doing something, okay? Now, here's kind of an important point, not to treat these as probabilities, because of course, you know, if you add up numbers, you might be greater than 1. Rates by themselves are not probabilities, but when you multiply them by h, then they're approximate probabilities. And when you multiply them by h and add a little O of h, then they are really probabilities. Okay, so what you do is you add up all of these rates, and you call this lambda I. Okay, and that's a critical quantity. It's the rate at which the state leaves state I. You know, now, if lambda I actually happens to be infinity, the process won't leave I immediately, so you don't allow this. So you don't allow to have that the sum of these rates diverges. Of course, the sum of a rate can only diverge if you have a countably infinite state space. Otherwise, it'll always be finite. Okay. And if lambda I is 0, then you never leave state I. I mean, that's an absorbing state. Okay. And then what you can do is you can build from that a probability. And you call this probability Rij. So that's a probability of, that's the ratio of Qij and lambda I. So lambda I was the sum of all of the rates. Okay. So with these probabilities, you actually have your embedded discrete time jump chain within a continuous time Markov chain. Okay, so if the Markov chain was specified by these rates, then these probabilities will give you some of the information. They won't give you all the information. They won't say how quick things happen. What they'll say, what are the probabilities of going from one place to another. Just to see this, let's go a second to this branching process. Okay, so the branching process seemed extremely simple. I mean, we spent 3 weeks speaking about a branching process at the start of the course, but this is kind of a very simple construction. Okay, so what is R from state n to state n plus 1? Okay, what we need to do is we need to do lambda n divided by lambda plus mu n. So that's lambda divided by lambda plus mu. Okay, so that's your chance of going from state n to state n plus 1. Now I'm going to take a break for a quick second because I've asked my children to remove the dogs, but they haven't. So I'll be back in 1 second. Sorry. All right, I'm back. Are there any questions? You guys with me? Do you hear me? Hello. Maybe I didn't unmute it. Oh, you hear me?
Yeah, all good, Yanni.
Okay, thanks. All right. Okay, so Madhus is asking, I don't get why the rates are indexed. So the rates are indexed because they're rates of transition from A state to A state. So just like you had in discrete time chain, you had probabilities, and you had the probability of transition from state I to J. Here you have the rate of transition from I to J. A rate by itself is not a probability, but a rate, once you multiply it by a small h or a delta t, then it's an approximate probability. Okay, so that's what the rates are. Okay. Now here's did that help? Okay, yeah. So here is a formal construction, and I'll let you read this, but please do and ask me questions later. And I'll get to this section now, computer simulation. Okay, so sometimes when you see a computer simulation or something, you kind of get a clear understanding of how it actually works. Okay. So here is one way to simulate a continuous time Markov chain. Okay, here's one way to simulate a continuous time Markov chain. So what you're going to do is you're going to generate independent standard exponentials. Okay, so standard exponentials, we mean they're exponential with mean 1. That means with rate 1. Okay, notice that the parameter of an exponential is called a rate. Okay, I mean, one way you can do this is by doing minus ln of the uniform. That's taking what's called the inverse probability transform. You might remember this from your previous probability course. Okay, now you take another sequence of random numbers and you generate transitions of a discrete time Markov chain. Okay, now what is happening in this discrete time Markov chain? This is a discrete time Markov chain with these probabilities. Okay, so the probabilities are given by the ratio of the rate of transition from I to J and the total. This is lambda as a total rates. Okay, so that's what you call your embedded Markov chain or your discrete time Markov chain. So, you know, you're already an expert in generating discrete time Markov chains. You've just done the discrete time Markov chain. And then what you would do is you would take Tn, which I guess I skipped here in the formal construction, and Tn is the time between two events of the continuous time Markov chain, and you'll take Tn to be your tau i's. Okay, or Tn would be the sum of the tau i's. Okay. Now, this thing is an exact simulation of a continuous time Markov chain due to this fact, which we saw in, I think it was SP2. I'm going to SP2 when we spoke about exponential random variables. And there was a fact that so theorem 2.1 here, I'm going to theorem 2.1 of SP2, okay? So when you take the minimum of n exponential random variables, then the winner of the minimum and the value that the minimum got are independent random variables. And the continuous time Markov chain, basically what's happening is because you're in state, now let's go back to continuous time Markov chains. So when you're now in state I, and you can go to state J or state K or state L, okay, at rate Qi J, and similarly, I won't write it Qik and Qil, then you have a exponential random variable taking you here, an exponential random variable taking you there, exponential random variable taking you there, and where you're going to make a transition is based on who won. Now, what is the probability of the winner winning? Well, that probability is exactly this. That's this Rij, okay? That was, if you go back to what I just was at, SP2, that is a probability of these kind of 3, or in general, multiple exponential random variables of having a win. And how long are you actually going to be here until the winner stays? Well, that's going to be an exponential random variable with rate lambda I, with the sum of the rates. So that's pretty much what's happening in a continuous time Markov chain. Okay. I mean, I think you'll see a few examples, and then you'll get a bit of more formal construction also from the other book. But in general, a continuous time Markov chain is like a discrete time Markov chain, where you don't speak about probabilities, but you speak about rates. And most of the time, you're going to stay in a single state until you make a jump. And the time between events is exponential. That depends on the state you're at. So I'll only give you a very quick guided reading through these 2 examples. So example, and please read through this yourself, the pure birth process. So something's called a pure birth process if you can only make a transition from state I to state I plus 1. So it's called birth if we treat this, in general, we call processes birth death. If we treat the state as the number in the state, as kind of the number of individuals in the population. Okay. So, I mean, the branching process was one such case, right? There was like the state, your state n meant there are n individuals in the state. I mean, the state doesn't have to be that. The state can be something else. It can be weather, right? Which is completely not ordered or something like that. But if you speak about processes that are birth death, then that means you can only make a transition at any given time from state I to state I plus 1, or maybe to state I minus 1. But in this process, you only go from I to I plus 1. And let's say that the rates have the following form. So lambda is a constant, and it's I to the power p, right? So all either Qij's are 0. Okay. And for such a process, you can actually compute the E of t of n, which is the sum of the nth jump, and you can do a few nice things. So look at that. Okay. This other example is much more general. And this is something called uniformization. Okay. So say now that the supremum over all lambda i's, remember lambda I is when we take state I and we look at the rate of transitions out of state I. Lambda I was the sum of the rates. This was our lambda I, the sum of the rates up here. Okay, that's lambda I. Okay, so say that the supremum over all states is bounded. Where are we? Here. Okay. I mean, if you have a finite number of states, that's always going to be the case. Okay. And even if you have an infinite number of states, that's why you need a supremum, then that means that the least upper bound is finite. Okay. It's not that this thing can kind of increase. In this case, you call this the maximal rate, this capital lambda. This is the capital lambda, the maximal rate. What you can do now is you can define another type of Markov chain, okay? A discrete time Markov chain. This is a Dtmc, discrete time Markov chain, okay? Up to now, everything for us with discrete time Markov chains. Now we're in continuous time Markov chain. So you'll define this discrete time Markov chain. This discrete time Markov chain will have a probability of going from I to j, which is Qij, not divided as we had before, not normalized by the lambda that's specific to I, the little lambda I, right? This lambda I was kind of specific to state I, but rather by this maximal rate, capital lambda. But the discrete time Markov chain will also stay in state I with probability 1 minus lambda I divided by lambda. Okay, 1 minus lambda I divided by lambda. So this is a discrete time Markov chain, which is different than this one, than the embedded chain, because here RII in the embedded chain was 0. Okay, in a continuous time Markov chain, you never move kind of from state I to state I. You just stay in state I until you jump. Okay, so if you look at discrete jump points, you'll never go from I to I. Here, you can stay in state I to state I. Okay, so this is a discrete time Markov chain. Now, we don't see this here, but it turns out that if you do this general thing called uniformization, and it's called uniformization because you've kind of made a uniform rate, which is a supremum of all rates. If you do this for a discrete time Markov chain, then many of the properties of this discrete time Markov chain will be like the original continuous time Markov chain. Okay, the original continuous time Markov chain was specified by these Qs. Specifically, one such property, which we haven't spoken about yet, is the stationary distribution. Okay, so then you could compute the stationary distribution of the discrete time Markov chain that has these transitions, and that's the stationary distribution of the continuous time Markov chain. Maybe it's a bit vague at this point. Sorry, I'm not very engaging with interaction today. Did you have any questions?
I just hope you put this lecture online sooner rather than later so we can review.
Will do after this. Yep, sorry. Okay. All right. Now we're moving on to the next thing, which is computing the transition probability. So I think at this point, what I'll do is actually, because I want you guys to get going on the reading, so let's look back at the self-study guide. So I've kind of given you an overview of section 4.1. Let me now try and in quick time to actually overview this whole thing. Let's see if that's doable. So treat the remaining 10 minutes as kind of an overview of this activity. And Xian is asking what is sup I in the notation? So sup I is a supremum over all states lambda I. So supremum is the smallest upper bound to this set. So basically, when you take a supremum of set numbers, you take lambda 1, lambda 2, lambda 3. Let's say if i's are really indexed by the natural numbers, okay? And this set can be infinite. And you'd say if there is a number L such that L is greater or equal than lambda I for all I, but L is the smallest such number, then that's a supremum. Okay, supremum you can think of as a maximum informally, but maximum, if the set is infinite, maybe there's no maximum. Okay, so there's no maximum to this function, to 1 minus 1 on x. Okay, for all real x, right? There's no maximum because I can get arbitrarily close to 1, but the supremum is 1 as the least upper bound. Okay, that's supremum. I hope that helped. Section 4.2, computing transition probability. So the focus of this section, the big thing you need to come out with this section is actually understanding how you compute this PTIJ, this transition probabilities IJ. And there'll be kind of two results. There'll be something called the backward equation, and there'll be the forward equation. Now, these equations are, you guessed it, your favorite differential equations. Here it is. Here is now the backward equation, okay? And the forward equation looks similar. And this is the forward equation, okay? So look, this is the forward. You've got the P here. This is the backward. You've got the P there, okay? And this is the derivative. What is this Q? This Q is is this matrix which naturally encompasses the rates, and that's called a generator matrix. Okay. So it turns out that if you want to see how probabilities evolve for a continuous time Markov chain, then they actually follow this differential equation, okay? Where PT is a probability vector, okay? PT is a probability of being in state, the ith index of PT is a probability of being in state I at time t. Okay. This is nothing but a linear system of differential equations, and when you get to such a system of differential equations, you might remember from math 2000, 2001, someplace else, etc., that you can actually solve it with a matrix exponential. Okay. So it turns out that you can actually find the transition probabilities by computing a matrix exponential. Only problem is this matrix exponential is only really well defined if your state space is finite. Okay, so for state space finite, this is all kind of a bit simpler. All the time, just like in discrete time Markov chains, all we've done really in the project, for example, was finite state spaces, okay? But you keep in the back of your head that you also have situations of infinite state spaces, such as was already the case in some of these examples, like in the branching process here, it's an infinite state space. Okay. But the good news is that when you're speaking about transition probabilities of the chance of going from state I to J, you get this guy. Okay. Now, what was that analog of this guy in discrete time? It was kind of simpler. You just took matrix powers, right? In discrete time, you want to know the probability of going from state I to J in 20 time units. You took the transition probability P and you took it in 20 time units. And you took it to the power 20, P to the power 20. Here you have matrix exponentials. So this is where you read about the forward and the backward equations, and we'll probably speak about that Friday as well. Now, the Poisson process can then be treated as a special case, and you actually can write the forward equations and the backward equations for the Poisson process. And this is kind of some of the basic things you need to do for this course, okay? Kind of taking a continuous time Markov chain and write the equations for it. And here's a Markov chain that's much simpler, the two-state chain, okay? So two-state chain is simply you're going between states, say, off and state on, okay? With rate lambda here and rate mu there. Okay, here lambda and mu are parameters. So that you can call that Q12 and that's Q21. Okay, so the two-state Markov chain. So you're basically, what this means, you're spending an exponential time in off, an exponential time in on, an exponential time in off, an exponential time in on. Okay, and you could also write the equation. So this is all kind of straightforward. And then this example is kind of nice because, you know, your states are not integers that have kind of a concrete meaning of being in a certain number, etc. Now, when you look at the generator matrix, so here I'm looking at the generator matrix of a continuous time Markov chain, just to be clear a second. So look, we spoke about those rates, okay? And you see, I'm saying now you're going to have a matrix Qij where you'll put the rate of transition from I to J if J doesn't equal I, and then you'll put here in the diagonal for J equaling I, the diagonal of the matrix, the point, the entry of the matrix where I and J are the same, you'll put minus lambda I. You got to keep in mind that from a modeling perspective, minus lambda I here does not add you more information because minus lambda I is just a sum of overall J of this guy. Okay, so you know you don't get any information from that. The reason you put in the generator matrix is so the forward equations and the backward equations look nice with this matrix, and then you can solve everything nicely. Okay, so it's not for kind of accounting of parameter purposes; it's for mathematical purposes. Now I'm saying this because here you're coming to an example of a generator matrix. So these are these four states where we call the states A, G, C, and T, A, G, C, and T. Okay, remember in a transition probability matrix of a discrete time chain, you'd expect these guys to be probabilities. Okay, each row to be probabilities. Not anymore in continuous time, these guys are now rates. So the rate of transition from A to G is alpha. Okay, alpha can be 7. It can be 19. It doesn't need to be a probability. And here you have a rate of beta. And here you have a rate of beta. So what do you have here in the diagonal? You simply have minus the sum of these guys. Okay, minus the sum of this guys, minus alpha plus 2 beta. So the sum of each row, and this guy is minus the sum of these guys, etc. So the sum of each row of a generator matrix is 0. Okay, a generator matrix is not a transition probability matrix. Okay, here, look at this generator matrix. What's the sum of each row? Sum these two guys, you get 0. Sum these two guys, you get 0. Okay, so the diagonals don't really add other information. Okay, but they are negative of the sum of the other things in the off diagonal in the row. All right, so you'll read through this, and then you get to branching processes. All right, so this is kind of an in-depth look at continuous time branching processes, but I'm quite sure that I suggested that it's just to skim the branching processes. Okay, so if you look here, SP4, just to skim the branching processes, but then make a digression in the process to the other book, MC2. So I'll steal another minute if you guys don't mind. So just let's look quickly at MC2. So remember, the Norris book is in general more, a slightly more rigorous book. And I actually want us just to get a kind of a loose feel for continuous time Markov chains at first. But it's pretty good to look at section 2.1 because it just speaks about Q matrices, about generator matrices. Now again, remember that here you can always think of the set I, which is a state space, as just a finite set, say the numbers 1 to n, and then you think of this thing as a matrix, but more generally it's a collection of numbers, okay? It's not, because I can be a countably infinite set, okay? So here you deal with generator matrices and just properties of general matrices, etc. So have a read of that. That's in this study guide, in the self-study guide, and specifically important to kind of do. This is actually straightforward linear algebra, but it requires some effort to do diagonalization. So we did this type of thing when we spoke about discrete time Markov chains, and we wanted to take the transition probability matrix to the power n. Now in continuous time Markov chains, you'll want to do something else. You'll want to compute the matrix exponential, e to the power tq. Now, matrix exponentials are just defined as a kind of a series of matrix powers like this when you normalize by k factorials. So if you're able to do diagonalization, again, yeah, you diagonalize q to be, these are going to be the eigenvalues, and this is going to be vector, these are going to be matrices of the eigenvectors and their inverse, then you can do the same type of thing. Okay, so this is diagonalization. That's why I suggested that you read that, specifically because of that bit. And I'll finish in a sec. So then the self-study guide also goes to something which is much more lightly written, and that's SWJ10. That's my book. And you can actually read that first, perhaps from the start. So if you go to SWJ10 and you go here to continuous time Markov chains. So here, in my draft book that is much less formal, I've tried to put kind of an informal introduction to what continuous time Markov chains are. And then this is a computational example that actually simulates a continuous time Markov chain. So it's probably pretty good to look at that one. And this is later on a simple Markovian Q. That's an example of a continuous time Markov chain. Look, again, you have a generator matrix, okay? Here you have states 0, 1, 2, 3, etc. 1, 2, 3. You have zeros everywhere except for these bands here. And look, you've got minus lambda and lambda. Sum of the row is 0. Mu, lambda, minus lambda plus mu. Sum of the row is 0, etc., etc. All right, so let's stop for questions. I apologize, I was a bit kind of like today. I will upload this lecture to YouTube ASAP. TJ and the rest. Questions? Yeah, is there an update submission? Yes, certainly so. And maybe I missed it at the start, or maybe you came a second late. So it's May 27th. May 27th.
Well, final exam, Yoni, do you set the date that we do that, or is that set by the uni, or when?
No, that's central exams. They employ 50 people to set the date for them. They're working on it as we speak.
All right, thanks. Very funny.
I wasn't joking. Yeah.
Just with that final exam, does that mean that like we could have the STAT3004 exam on the same time, or like on the same day as like another exam, for example? Or...
No, so yeah, I mean, I was kind of bashing exams for the 50 people, but they ideally make sure that that doesn't happen. They can't tend to any person, but they're actually running an integer programming problem to make sure the minimization of clashes. Now, since we have a 24-hour exam, there might be such a situation. And if anybody is in a tight situation, I mean, this is an exceptional semester with exceptional circumstances, and please write me an email so I know. I'm not sure what I could do in such a case, but at least I know, and I'll be aware of it. So I'll try to at least be, do my best to see if that's a problem.
I think it's kind of common sense, but the 24-hour exam would be harder than a normal exam we would expect to be done in 2 hours in the exam conditions. Would that be right?
Yeah, so the 24-hour exam will have about 60 or 70%, which is equivalent to a 2-hour exam, and then just a bit more, which is slightly kind of a heavier tail. I mean, in general, whenever I do exams, I always try to kind of keep somewhere between 50 and 70%, which is rather straightforward, and then you put about 30% or 40% that's kind of a bit harder, right? Now there's a bit more time, so the harder can be slightly harder, but it's not something that you're supposed to suffer through for 24 hours.
Thanks.
And it's with open material. More questions? Okay, so again, I apologize for not putting up your project yet. I just didn't, well, I really wasn't able to. I should have, but I hope you'll have enough time till May 27th. So it should be up later tonight or tomorrow, and same with lecture videos. And I'll see you guys. Oh, there's a visit hour today at 2. Feel free to come to that hour and ask me specific questions about what we've just done, if you see fit, if you're already able to push on the self-study there. All right, so see you everybody. Bye-bye.